Okay, we have another quiz video. Here, a very straightforward question. Um, we have a parallel plate capacitor in this case. You're given the capacitance, and you're supposed to find out some features of that particular capacitor. So give it a shot, check the end of the video, and come back if you need. Okay, so let's begin. We're going to take our parallel plates here. And we'll talk about voltage as connecting a battery, okay? So, we're given capacitance as 1.2 nanofarad. We're given the charge as 0.8 microcoulomb. And we're given, excuse me, we're given a plate separation distance in part B, so we'll need that later. And I'm going to write this as 3.5 times 10 to the negative 4 meters. Okay, our first question is what the potential difference is. So the equation that should probably come to mind immediately is the definition of capacitance. Right? So if we rearrange this equation, that gives you the voltage across the plates directly. Now, remember that this Q actually represents, we have like some amount of charge on one plate and the equal amount of opposite charge on the other plate, right? So this Q is not, you don't have to worry about both of these Qs because it represents the amount of charge that was removed from one plate and put on the other plate, right? Okay, so the voltage here, then, if I'm double checking my math, yeah, should be equal to 0.8 e to the negative 6 coulombs divided by 1.2 e to the negative 9 farad, which gives us 667 volts. Okay, so part A, the potential difference between the plates, 667 volts at 3 significant figures. Okay, clear this out. So for part B, we're supposed to find the electric field inside, and we're given a new bit of information here. So in order to find this, we would be interested in the equation, voltage, and we can actually just refer to this as the magnitude of the electric field. Don't worry about the negative sign there. And our delta x, the distance between the 2 points, is actually just the plate separation distance d, right? So, okay, this is pretty straightforward. The strength of the electric field is then given as the voltage divided by the distance. And we've already calculated our voltage, 667 volts divided by 3.5 times 10 to the negative 4 meters. That gives us 1.91 times 10 to the 6 volts per meter. Okay, so that's part B. Now our third part, part C, what is the area of the plates? So there's actually a couple of ways that we could go about this. One of them is by looking at the equation for a parallel plate capacitor. And we look at charge divided by, whoops, that's not right, it's not charge, excuse me, epsilon naught, area divided by distance between the plates, right? Okay, so the next way is that we can look at the electric field, which we just found out in part B, which for a parallel plate is given as Q over epsilon naught times the area, right? So both of these allow us to calculate area. A little bit of algebra will give us that the area is either equal to the capacitance times the separation distance over epsilon naught, or we can say that it is equal to the charge divided by epsilon naught times the E field. Okay, so they should give us the same answer. This one gives us 0.0475 meters squared, and this one gives us 0.0473 meters squared. This actually is a little above 3 and this is a little below 5, so it would probably be fine for us to take the area to be 0.0474 meters squared, and we can also put that into units of centimeters squared if we want. Remember that we need to convert that there are 100 centimeters in a meter, but there are 10,000 square centimeters in a square meter, right? So we have to convert twice, one for each of these units, right? So part C would then give us that the area is about 474 square centimeters. Okay, so I'm going to wrap this up. Okay, there's our answers. If you got something else, then go back, take a look at the video.